Hello students, I am Tulika Banerjee. Today I bring you a learning module in BSc Forensic Science on behalf of the content writers Dr. GSOD and myself on an important unit of forensic science, which is internal ballistics, in which we will discuss in brief about the concept of internal ballistics along with ignition and shape and size of propellants. We will wind up this module with discussion on various factors affecting internal ballistics. Let's start our module with a look at what we are going to learn today. Dear students, let us now start with the introduction of this module, that is internal ballistics. The term ballistics is derived from the Latin word ballista, which refers to a cross bow-like device for throwing stone by means of twisted ropes. In order to understand the elements of ballistics, it is divided into three parts, such as internal ballistics, external ballistics, and terminal ballistics. Internal ballistics is the study which deals with the motion of the projectiles in the bore of the weapon, whereas external ballistics deals with the flight from the muzzle of the weapon to the target. This indeed is a terribly complicated subject involving parameters such as shape of the bullet, sectional density, atmospheric conclusions, and even rotation of bullet in larger caliber weapons. With the advent of powerful personal computers, the complex calculations have become quick and accurate. The terminal ballistics, that is the third element of forensic ballistics, it deals with the behavior of missile once it reaches the target and strikes it, such as wounding capabilities, and includes its performance in water, soil, brick, concrete, wood, and other bullet resistant materials. So, all these three elements together forms the fields of ballistics. When this knowledge of ballistics is included in criminal investigations, it is then termed as forensic ballistics. Here in this module, we will mainly emphasize upon internal ballistics. Let us now study about ignition of propellants. Nitrocellulose as propellant, if ignited in an unconfined space, will burn gently. The heat and pressure built will accelerate the rate of burning exponentially if it is in a confined space. The products of combustion in case of nitroglycerine are carbon dioxide, water vapors, oxides of nitrogen, nitrogen, and heat. 1 gram of nitroglycerine will produce 1000 cubic centimeters of gas at normal temperature, that is 0 degree Celsius, and a pressure of 760 mm. The heat given by the reaction is also tremendous, about 1000 calories. The temperature may cause 3000 degrees centigrade. Only a portion of this energy is converted into kinetic energy of the projectile, and most of it is wasted. In a weapon, the propellant is confined in a cartridge case, the mouth of which is closed with a bullet. The round of ammunition is then supported by the chamber walls and the standing breech of the weapon. Under these conditions, the pressure built up will continue until it is sufficient to overcome the inertia of the bullet and starts its acceleration down the bore. The heavier the bullet, greater will be the resistance and higher the pressure. When the propellant burns, it gives rise to gases and they remain confined completely within the cartridge case, and pressure is exerted equally on the base of the cartridge, its walls and the base of the bullet. Once the bullet starts to move, the volume filled by the gases increases and the pressure starts to fall in accordance with the gas laws. Next, dear students, we will be now studying about the types of propellants. In modern propellants, moderating the propellant grains can compensate the fall in pressure. This moderation involves the addition of grains. In some propellants, the grains are also pierced with holes. There are different types of powders, namely progressive powders, degressive powders and constant burning propellants, which has been explained one by one. First, we will be dealing with progressive powder. For some weapons, particularly in respect of shoulder arms, it is desirable the pressure should not develop suddenly and the increase in pressure should be gradual. Dense and bulk powder, when ignited, burn rapidly with the result that the projectiles receive a big push. Gradual development of pressure not only provides better velocities but also prevent quick wearing out of the barrel. Progressive powders are manufactured to suit the needs of a particular weapon by controlling the shape and size of powder grains. Examples include powder grains having multiple perforations in them. The next type of powder is the degressive powder. In the case of degressive powders, the shape and size of the grains are kept such that as burning of propellant progresses, the rate of burning goes on decreasing. For example, in case of non-perforated powder grains. The third type is the constant burning propellant or the constant burning powder. In this type of propellant, the powder grains contain a single perforation and the total surface area burning at any instant is constant. Example, single perforated grains. The moderation of the propellant grains no doubt has an effect on changing the rate of burning as the propellants are consumed. As a result of this, the internal pressure does not drop so drastically once the bullet begins to move. The moderation of the propellant has to be carefully regulated to ensure that they are totally consumed just before the bullet reaches the end of the barrel. Any propellant which is not consumed before the bullet exits the barrel with result not only in low efficiency rate for the cartridge but will also produce a large muzzle flash which can be extremely disconcerting when firing at night, as it has the effect of destroying the shooter's night vision. Next, we will be talking about the geometry of gunpowder. Burning of propellants is a function of geometry of gunpowder. Certain terms concerning burning have been explained now. First, I will be taking up combustion. It takes place when the reaction of the burning propellant or substance arises out of its contact with the air in an open space. If the reaction takes place in an enclosed space, this space should be large enough for the heat generated to be dissipated and the gases produced will disperse without generating any significant increase in the pressure. The spreading of fire is brought out by the gradual heating of the surrounding area. Next is deflagration. It includes rapid and violent burning and is an intermediate step between gradual combustion and detonation. Deflagration can also be understood in simpler terms as comprising of layer by layer burning phenomena, wherein the lower layer of the propellant reaches the ignition temperature and starts burning. After that, the very first layer has burned completely. The second subsequent layer will reach the ignition temperature and starts burning, and so on. This is caused by the acceleration due to gradual heating up or by the increased pressure of the gases produced by decomposition of the mass according to the conditions prevailing in the explosive system. Next is detonation. It takes place when the explosion is extremely rapid and the formation of gases is almost instantaneous, transmitting shock waves, which are also known as explosive waves. Ballistic powders are capable of producing large volumes of high temperature gases in a very short period of time by means of deflagration. The propellant charge is composed of quantity of grains that are ideally of the same shape and size. Solid cylindrical grains present a smaller area as burning progresses. Cylinders with certain perforations along their length presents nearly a constant surface area, and propellants of this shape are called as constant burning propellants. With multiple perforations, the amount of propellant burned increases as burning progresses. In forensic terms, ballistic advantage of the latter is that it generates gas at a lower rate initially when the total volume behind the projectile is small, and produces gas at an accelerated rate as the projectile gathers velocity and creates greater volume behind as it moves through the barrel towards the muzzle to escape in air. There are various factors which affect internal ballistics. These factors include combustion of propellants and barrel length, atmospheric temperature, shape of the cartridge case, barrel pressure and dimensions, velocity of bullet, bullet jump and vibration. Now, we will be taking up all of these factors one by one. There are wide variations in the rate of burning of the powders. Some powders burn quickly while other burns slowly. Various firearms require different burning rates. For example, in pistols and revolvers, a very quick burning powder is needed so that the powder is converted into gases before the projectile is pushed out of the short barrel of the firearm. If slow burning powder is used, the projectile will not acquire the desired velocity. Likewise, if quick burning powder is used in long barrel firearms, the projectile will not receive sustained amount of pressure. Consequently, for the maximum pressure, the projectile will have a lower velocity. If a powder with appropriate burning rate is used, the projectile can be given higher velocities for the same maximum pressure. The rate of burning has to be related to the length of the barrel. The pressure in the firearm cannot be increased beyond a certain limit, and the limit is determined mainly by the strength of the barrel and action of the firearm to withstand the pressure. Ammunition is manufactured to give the desired velocities and pressures at a particular atmospheric temperature. If the temperature differs only slightly at the place of the use, the ballistic aspects are not seriously affected. If temperature variations are substantial, example in Ladakh or in Rajasthan desert, they affect the ballistics aspects of the ammunition. In hot places, the pressures developed may be excessive and the firearm may burst. In cold places, the ammunition may develop low velocities. In Indian ordnance factories, they manufacture most of their ammunition with a temperature tolerance of minus 52 degrees Celsius to 72 degrees Celsius. It has been found that the variation in velocities because of the temperature is about 1 meter per second per degree Celsius. It has been observed that if there is an abrupt junction of the neck and the case, the rounds develop greater pressure for the same quantity of powder. The combustion is more uniform. It appears that abrupt neck joint deflects the hot gases inward. The hot gases quickly ignite the powder charge in every nook and corner. Thus, correct initiation and complete combustion of the powder charge takes place inside the cartridge. It reduces excessive heating and wear and tear of the barrel. Two of the essential parts of a weapon are barrel and action. Manufacturing processes, specifications and tests are conducted to assess the limit of barrel life and non-failure of action. Before any barrel is accepted for use, it is proof-fired with a high load test cartridge, which is capable of producing at least 40% more pressure in the barrel than the lead which is intended to withstand. To have an idea of the magnitude of pressure developed in a barrel, I will quote an example. A service rifle is expected to withstand a barrel pressure of 50,000 pounds per square inch, but test fires would be conducted with ammunition giving rise to a pressure of 70 or more thousand pounds per square inch. The objectives of such post-manufacture tests are to find any fault in design features and to correct them and establish its identity or suitability for a safer use. While in non-standard weapons or country-made firearms, failure of barrel takes place quite frequently. Tremendous pressure is developed in the barrel of a firearm during the firing process. There are several factors responsible for it. Some of the important factors include the quality and quantity of powder charge, the available space for expansion of gases produced, the chemical nature of the powder, and the surface area of the burning propellants. Different types of powders, namely progressive powders, degressive powders and constant burning powders, produce different maximum pressures. Maximum pressure developed is considerably less in case of progressive powders than in other powders. Formation of excess pressure may burst the barrel of the firearm or the firearm itself, causing at times even fatal accidents. Such cases comes up in criminal investigation. Likewise, the development of low pressures in some firearms used in commission of crime may lead to unexpected types of injuries which require careful evaluation. Hence, it becomes essential to measure and understand the formation of pressures inside the barrels. There are additional factors also which contribute to the development of pressure to some extent, namely shape of the cartridge case and depth of grooves in the barrel. For the same quantity of powder, greater pressure will be developed if there is an abrupt junction between the neck and the case. The designers of firearms and ammunition have aimed to hurl projectiles with a suitable velocity so that they strike target at a particular range, keeping in mind to strike a balance between charge weight and velocity of recoil of the firearm. Since every action has an equal and opposite reaction according to Newton's third law of motion. The muzzle velocity depends on several factors, namely quality and quantity of powder, barrel length and bullet fit, mass of the bullet and its shape, as well as the bore of the weapon, etc. If a stone is thrown manually or through other means, energy required could be supplied by the person throwing the same, because it is small. In case of small arms, the velocity generated is much higher, so chemical energy is harnessed for the propelling of projectiles. As soon as the projectile or projectiles starts to move in the forward motion or forward direction, the firearm moves backward and upward. Movement of the barrel is called as jump. The jump is noticeable in handguns. A double barrel gun suffers sideways vibrations. The vibrations and the jump are considerably affected by the manner in which the firearm is held. These vibrations are comparatively smaller when compared with those caused by the movement of projectiles in the barrel. Some vibrations are caused as soon as the release and striking of hammer takes place. Movement of the firearm takes place in an upward direction. As has been told to you earlier, the force which acts on the rear side of the bullet to propel it forward is also exerted on the base of the cartridge case to move it backwards. It is this force which causes the weapon to recoil. This force not only drives the firearm to the rear, but because the barrel is situated above the hand and therefore above the rotational axis of the wrist, it also moves the firearm in the upward direction. As the bullet is travelling down the bore during the period in which the barrel is lifting, it will strike the target above the point at which the barrel was pointed when the trigger was pulled. The actual time the bullet remains in the barrel is extremely short and is in the order of 0.001 seconds, but it does not change the situation as the muzzle lifts the point of aim by a fraction of inch. This does, however, has a pronounced effect in the striking point of bullet and change the impact point by more than 1 inch at 100 yards. In most of the standard weapons, flight is regulated for a set of certain bullet weight travelling at a certain velocity. The situation in case of non-standard weapons or country-made or improvised weapons is quite different, since no such setting has been seen and thus efficiency remains quite low. It is quite interesting to note that the heavier bullets strike above the point of aim and a lighter one below. This is exactly opposite to common sense would indicate. The field of ballistics comprises of three main elements named as internal ballistics, external ballistics and terminal ballistics. As you all know, internal ballistics is the study which deals with motion of projectiles in the bore of the weapon, whereas external ballistics deals with the flight from the muzzle of the weapon to the target. On the other hand, terminal ballistics deals with the behavior of missile once it reaches the target and strikes it, such as wounding capabilities, and includes its performance in water, soil and brick, concrete, wood and other bullet resistant materials. As the study of internal ballistics is related with the study of motion of projectiles within the barrel of a firearm, So, it becomes an important factor to know the various types of propellants and their shapes. Moreover, factors which affect internal ballistics comprise of combustion of propellants and barrel length, atmospheric temperature, shape of the cartridge case, barrel pressure and dimensions, velocity of bullet, bullet jump and vibration. These factors are studied with the purpose to know more how a projectile behaves when it is within the barrel of firearm.